The question that is considered for discussion in today's short lecture is why the single-phase induction motor is not self-starting. Now, as we know, a single-phase supply, you can think of a winding inside the motor which can take that single-phase supply. Obviously, one phase means one winding we have to make. And here there are two poles shown, the simplest of it. You can think of multiple poles, but a two-pole structure is structure of the stator is selected to make the explanation simple. The second one, the rotor is a squirrel cage rotor, which is short-circuited at the ends, a common structure that is for the squirrel cage. Now, the next thing is how this is not self-starting. And normally, when you think that with provide AC supply, the motor should work, or simply should work with the single-phase winding. Now, we'll see how that is not happening. For that, let us see how, say, for example, the AC is varying or AC supply is varying. So we go back, or we say we think of say two half cycles generally. So the AC may be having say positive and negative directions. I mean two directions. So for a simple structure as AC here, you can think of this positive as a negative half cycle. So we are doing this just to see how this can actually change our, understanding. I mean, this can happen. So say, for example, this path, I'm passing through all these windings and then coming up. Say in the positive direction, let this be the positive direction or this direction. So for one half cycle, you have this. It's moving like this. And for the other half cycle, that is the green portion, the negative part, say, so here, it is happening in the other direction. So you have two cases, that is one in this, and so as time passes, everything happens in that sequence. So you can see that by the nature of the winding, sometimes, say for example, in the first case, the blue case, you can see that the flux is actually varying or is oriented in a particular direction. So according to that convention to find out the north and south poles, you can see that this is actually what we call say in this direction. See, obviously it is going to be in this flux in one half cycle. And when the time is on the other half, when the time period is in the second half, the direction is going to be, say, something like this. You just check whether that is holding. So the idea is that anyway you obtain a continuously varying, say, sometimes here, sometimes. So it just oscillates between two segments. That is, say it is, say, as if it is, you can say it is varying in this direction. Sometimes to here, and goes in this direction, reaches the maximum value, then starts to decrease, and finally it zero value, then advances in the other direction. So the flux is varying like this, and the impact is that these conductors here does experience a change, but that is just creating an effect wherein it doesn't have a torque being introduced in a useful manner. Then you can see the direction. So basically, in a motor, for the rotor to rotate in an AC machine, we have seen that a revolving field is necessary. So something has to guide the rotor conductor. So that is the field created, a revolving field. So here in this single-phase induction motor, as we have seen here, this uh, um, I mean, this uh, this this is actually a varying quantity, a pulsating quantity, not a circulating quantity. So what here is happening is a pulsating field, and it doesn't create that rotating effect of the field, and then rotating effect means that conductors will try to follow the path of the field due to Faraday's and Lenz's laws application. You can see that. So this is very simple. So we are seeing the question why it is not starting. It's a pulsating field that is produced in a direction, not able to create a revolving flux. So that doesn't create the necessary torque for the. So sometimes torque in one direction, sometimes the other direction. It just changes. So that is the reason why single phase induction motor with the normal winding is not self